Live. Siamo partiti. Okay, here we are. And Davide, do you want to share your screen?
Yeah.
And let us know briefly what you're going to present today.
Yeah, we are gonna introduce to continue the introduction to Transformers, and yeah, the last time we left explaining the attention mechanism. Um, in this today we will discuss about some limitation on Transformers, and then we're gonna introduce vision Transformers. That is the application of this architecture to computer vision, basically.
Okay.
So
Vale, we don't see you anymore. Can you enable your screen, please?
no, I see Valeria.
Okay. Excellent. Okay, now I see Valerio. Very good.
Okay. So last time we said that the attention layer is able to estimate the interaction between the words in a sentence, for example. So at every time step, the transformer architecture makes a comparison among the different words. So in this perspective, you can see the limitation of transformers. That is that the computational runtime complexity of the architecture is n squared, where n is the number of words in the sentence. And so this is the main limitation of this architecture. Several papers have been published lately to try to solve this problem, because this issue slow down largely the efficiency of this architecture.
Can you zoom into the PDF, Vale and Davide, so that we can see it a little bit?
Here the n is the length of the sequence. So in this example, the length of the sentence, so the number of words in the sentence, and d is the size of the embedding of the word. So every word is expressed with a word embedding, and d is the size of this embedding vector.
Yeah.
So there is a sentence, and the sentence could be, I don't know, this is a sentence, right?
Yeah.
The sentence, go ahead.
Yeah, the sentence length is like 5, 6 words. I don't see your screen, Luca, but
yeah, it's four words.
4 words. So n in this example is 4, and as in every NLP task, each word is described with an embedding, a word embedding.
Yes.
And D is the size of this embedding. Usually is a number from 100 to 1000.
Okay, so we have this embedding space, this space of embeddings, and so each of these words are projected into these embeddings. Yeah. And this embedding for the moment in my screen is 2D. Okay, so 2 dimensions. So it's D1 and D2, but what you're saying is that the embedding has big D dimensions and typical big, actually D, small d dimensions, right?
Yeah.
Okay, very good.
If you are watching my screen, here there is a comparison between among the different architectures. So, for example, in recurrent architectures like LSTM, the square is on the embedding side, because you are running through all the words one by one. So the runtime complexity is just linear in the number of words. but is a square, is a squared in the sides of the embedding vector. On the other end, the convolutions are squared in the sides of the vector, because you can see a sentence as basically as a tensor, right? Where there is the length of the sentence on one dimension. There are other two dimensions that is the sides of the embedding. If you want to estimate the interaction between among the different words, you have to put two dimensions for the embedding side.
Okay.
And K is the filter size of the convolution.
K, you said that K is what? The filter size of the convolution.
Yeah. So as I said, several papers in the recently tried to solve this problem, like they published line former, pair former, niece former. There are different variations that try to compute attention without this square complexity. But there I would like to focus on the application of transformers on images. There's been a lot of movement in this direction lately. Transformers are designed to.
Can you zoom in, please?
Yeah, to deal with sequences, right? Because they are designed to handle sentences. So how could we manage to transform the analysis of an image into a sequential task?
Images don't have they're not sequential data, but at the same time, there is some spatial correlation and some, it's not a sequence, but there are some regions that are homogeneous. They are corresponding to specific regions, to specific objects. So I guess that that sequential data or that correlation and redundancy can be found in, within a specific image, within object or regions of specific image. Is that correct?
Yeah, exactly. They basically divide each image in 9 patches, as you can see here. And so each word in the NLP task is a patch in the vision task.
But how do they decide which will be the first word, aka the first patch?
They just decide a convention. So the upper left patch is the first one. The upper center is the second.
Okay.
So let me rephrase. So what you're saying is that in transformers, in text, when applied to text, transformers deal with sentences and with words in particular, and in images we have patches. Is that correct?
Yeah.
Okay. Yeah. Then.
So since they are still images, even if they are more they are reduced in size, the patches are still images, right? So they just flatten these patches. So they have 16 per 16 frames, and they just flatten these frames. So you have 256 size vectors. Each one of these patches is a 256 size vectors, right?
Okay.
And so they, in this way, basically they have their word embedding to feed into the model. They add.
They extract these patches homogeneously in the image. They don't do any. They just crop the images into patches, and that's it.
Parts. Yeah. And to this embedding vector, they add a positional embedding.
Okay.
So, because as we have seen before, the attention mechanism is not aware of the position of each patch.
Okay.
So you have to indicate the position, and so they add like a tag to describe that this is right. This is exactly the patch number 1. This is the patch number 2, and so on. Yeah, and then
Okay.
they feed this.
I have a question.
To the transformers.
So in terms of so when we're dealing with text, we don't have the positional embedding problem, right? Because we already have the sequential information of each word in the sentence, right?
No, actually, there is the same mechanism in the word embedding in the empty task, but there is the same mechanism.
Okay. And what is so? I'm trying to just derive the differences between text and images. So one is obviously the fact that we're dealing with patches. From a positional embedding point of view, it's kind of the same. What else? How they differ? Do they differ, the two use cases?
There is no difference.
There is no difference. Okay, even better, easier to understand.
As you can see, the difference from this architecture to this one is that here you have only the encoder part, because image classification is not a sequence to sequence model, right? Because in this example, they use transformers to translate a sentence into another language. So they had to use a decoder to find the right word in that language. But in this example, they just use the transformer as a feature extraction model.
Okay, so they only use the encoder because they don't have to do, they don't have to do any translation. Yeah, fair enough.
I was wondering if maybe they could create features. They can for the same image they could use different position. Use different position IDs, different position conventions. So the first time they start from the top left. In the second time, they start from, I don't know, bottom right, and maybe then fuse all these embeddings.
I'm not sure to have got your point.
Since right now they are considering only a single convention, so the top left patch is the patch number 0. Then we have patch number 2, and so on. Maybe we could think to use different conventions, extract all the features using different conventions, and maybe fuse or features extracted from different conventions.
Yeah, I don't know if it could improve the performance of the model. I'm not sure about it.
Yeah, just something that I had in my mind.
Yeah, and here you can see an interesting thing, that is the difference between a convolutional neural network and the transformer architecture. In particular, this chart here. This is the average distance in the attention mechanism. So here you have the depth of the self-attention layers. So here there is the layer number 1, the self-attention layer number 1, and so on until the 20th layer.
Mm-hmm.
So in a standard convolutional neural network, since your filter size is limited, you can attend only the pixels close to you, right? And so you can see my
Yeah.
okay. So in a standard convolutional neural network, the curve would be like this, because you can see to very far away pixels only at the end of the convolutional part of the network, because you reduce the size of the matrix.
Okay.
And so at the end you can see the very far away pixels. Instead, in the transformer architecture, you can attend the different, very far away pixels since at the very beginning of the network.
And this has a major advantage because you can, the features that you extract early in the net are, they are summarizing bigger areas in the image. So maybe their information content is higher in very early stages in the net.
This limitation of the proximity of the convolution neural networks is overcome in transformers, in my opinion, because you can find patterns far away from a specific pixel.
Okay, so in this sense, are they more? I mean, full connectivity is the top layers or the first layers are more connected than in standard CNNs.
Yeah, exactly.
Okay. All right.
And here you can see that this architecture is in line with the performances of the best convolutional neural network in ImageNet.
Hang on a second.
They do even better.
Hang on a second. So what is the advantage of, so if the performance are, so first of all, we're talking about classification tasks here, right?
Yeah.
So from a classification perspective, what are the advantages of transformers versus traditional classifiers?
As we said, they can look at very far parts of the image and find patterns between them, and they are sought in the image classification task, because you can see here their visual transformer outperforms the ResNet in all the tasks, in all the data sets that they tried.
Well, hang on a second. So let's have a look. So you said it outperforms ResNet?
Yeah.
Yeah, but it outperforms, I mean, I wouldn't call it outperform. I mean, it's very, very, very small, the difference between ResNet and the transformer, isn't it?
It's a
1 point in ImageNet.
1 point.
Okay, not that small.
I mean,
not that small. Yeah, it's a little bit. And what is that baseline? ResNet 152.
Yeah, I think it is the current best model in the convolution.
Okay, fair enough. Fair enough. Yeah, I was looking at the wrong. And what is that noisy student? EfficientNet L2. Okay. So it's on par with EfficientNet L2.
Yeah, kind of, yeah.
Okay. And from a computational standpoint? How do they compare with ResNet?
I'm not sure about it.
There was that TPU core days as last row of the table.
Yeah.
Yeah. And it seems that
Yeah.
it.
But I think this is about the training phase. It's not about the inference.
Well, but the train is something interesting, right?
Yeah.
It's four times less than efficient than
That's
the rest.
interesting. Yeah, that's interesting. I mean, it's a significant reduction in training time.
But I don't know if we can afford the 2,000 days of TPUs.
Well, not at the moment. Okay, excellent. We're almost out of time. We have another couple of minutes. Davide, do you want to add any other final thoughts and any observations about this paper, and more broadly speaking about the applicability of transformers in vision?
I don't know. I don't have a really specific opinion. I think that it's obvious that transformers are very powerful because their inductive bias is very lower compared to convolution, neural networks, and LSTMs. But I think that there is a lot to do.
And in text that are very powerful and very effective because of the tasks because of the problems that you can solve with text, specifically with translation, with summarization. So there are very specific problems that make transformers very attractive in text and in NLP, right?
Yeah. I don't know. I think there is a lot to do in terms of efficiency because you cannot. There are still some limits in terms of computational efficiency, and I don't have a really specific opinion.
Okay, and maybe discover new applications. So these are the two main limitations about this, about the application of transformers in vision. Excellent. Okay, so thank you very much, Davide. Thanks for this. So what are we gonna do next, Valerio? And we're talking about this Friday, right?
Yeah, I was thinking about showing an example of using SageMaker, Amazon SageMaker, to train NXGBoost classifier, binary classifier.
Nice. So it's going to be an hands-on demo on how to use Amazon SageMaker to train an XGBoost.
Yeah.
Binary classifier. Awesome. Guys, thanks a lot. And I'll see you Friday.
Bye-bye.